All right, so I'm going to talk about secure by design. So as Julie said, I work for Carnegie Mellon University, one of the top leading schools in both artificial intelligence and computer science. Specifically, I work for the Software Engineering Institute, a fairly funded research and development center. It's been around since 1984. All right, so after that stuff, what's important from a program or an enterprise? So if I own, a car manufacturer, like Julie just mentioned, or a program with just building a weapon system of that nature, what am I focused on? Like you really are focused on three main things. One is why you exist, right? And for whom you're developing your products for. And then you're also concerned about how you are able, your ability to deliver value, right? Kind of usually refer to that as your pipeline or your CI/CD pipeline. And then you have the product itself, that thing of value that you are delivering to your customers or your user base. And from that area of concern, you really have two main challenges. One that I'm going to focus on today is really the cybersecurity threats of both the pipeline and the product, right? Traditional software security really thought of it in terms of network security, or have my product, have my application, say that's my castle, and I build a moat around my castle. How do I defend my castle? In today's world, with tightly integrated, CI/CD pipelines, right? What we've actually done with this type of integration of both our development environments and our product and our operational environments is that we basically build these super freeways across our moats into our products, right? And so how do I have to secure both the product and the pipeline, because I have exponentially increased the attack surface of my product. Because I can attack the development environment to get to the product, and I can attack the product to get back to the development environment, because they're tightly integrated, they're tightly connected. The second challenge I have is that I don't live in a static world. Things are constantly changing, right? My process, my tools, the engineering techniques, my staffing. And so these things also impact your ability to build and design and maintain a secure system. And to make things harder is all the adversary needs is one mistake, one opening in your armor and your defenses, and they're in, right? And to give you some statistics, right? 9 out of 10 breaches are due to defects in design or code, right? 56% of developers struggle to prioritize vulnerability fixes. Some of the more disheartening facts, right, is 90% of organizations knowingly release vulnerable applications. So they know it's weak, they know it has issues, and they release it anyways, right? 57% of vulnerabilities are left unresolved by developers, right? Right. And the last one, 60% of data breaches are caused by failure to apply available patches, right? Why patches? Well, it's not just updating my current operational software, but it's also using the latest libraries. And we'll talk about that when we get to third-party software issues. And the cost of businesses, right? On average, a data breach costs a company almost $4.5 million. It's even worse for healthcare and financial sectors. I find, last time I read all these, last couple I find really ironic, right? 47% now have a policy to pay cybersecurity ransoms. 82% of companies surveyed say that they paid for stolen data, but out of all these people, only 8% have actually gotten their data back. So people pay, they don't actually get their data back. So it's a big issue. And so secure must be engineered into the application, right? It can no longer wait until I build a product and then worry about defending that perimeter, building that moat, right? And so the three main areas of concern that I'm gonna focus on today is really that third-party software, why quality is important, and then what secure engineering techniques and practices you can build into your overall software development lifecycle to help you build a secure system by design, right? So the first one, third-party software. So in general today, software isn't built from scratch. It's built by bringing pieces together, right? Most applications are too large or too complicated for any one person to build. And some data, 90% of modern applications are assembled by third-party components. right? And why do we do that, right? One is it, amortizes our expenses. It provides, that low cost in terms of, why would I build that in which is a commodity versus building that in which makes me unique or adds specific value to my specific customer system, right? A quote here, right? Developers are gorging themselves on an ever-expanding supply of open source components, right? So it's not just third party, but third party is both that in which you buy, but also the open source. Both have risks, both have issues, right? Now people are starting to really take notice of the software supply chain. An example here is the Office of Management and Budget, 2022. They established a memo that says basically you need to use, the NIST supply chain security and secure software development framework in building software. And again, why does that matter, right? Well, so Log4j is a really famous example of a library used by a lot of applications. It's used by Microsoft, Apple, Amazon, right? All the big name companies, they use this one specific library to make their logging management easier. But it was vulnerable, right? And so it impacted, the entire industry because they used a third-party software that had a vulnerability. So you have to worry about, you have to think about these things, right? The cost of it, right? Probably 63% of applications have third-party code with flaws in it, right? And so how do I begin thinking about that? Well, I can Google open source or library, how do I do this? But should I use it, right? Should I just use a library because it's the most popular, right? Well, what makes things popular is people keep using it. It doesn't actually make it secure, right? There might be a different version of that software that's much more secure, that's actually patched some of these vulnerabilities, but people keep using that old one because it's the first one that comes up in their search, right? So things to think about, right? If I'm procuring this third-party software, right? Evidence of suppliers' capability, right? Are they following good, secure engineering practices and they're building a good product, right? Evidence of product security, right? The product that they build, does it have acceptable security, controls? Does it have password protection? Things of that nature. Methods of transportation, right? How do they distribute that software? Do they just email it to you? Do you have to download it from a secure website? Is it doing hash comparisons? Is it comparing, making sure that executable has not been tampered with, right? And then evidence of operational control, right? Is it fit for purpose? So some criteria one can use is really looking at, and here's some, some more documents and a memo that came out. But here's the list I was thinking about, right? So one, especially for open source, is thinking about what's the number of maintainers, right? Is this application only developed and maintained by one person, right? Or is it multiple people, right? How often is it being updated? Are they keeping up with issues and reports of defects and security issues? Are they using peer reviews, right? One of the things people brag about open source is that it's open. Everyone can look at it. It's, no one's hiding anything. Problem is, if no one actually looks at it, it's not actually adding any security to you, right? So is it going through peer reviews? Are people looking at the actual source code and looking at, is this written well? And the other part is, binary artifacts without source provenance, right? Are they just giving the binary? Should I be using that? Or really is a better practice is to use the source code and build your own binary, right? And the other is who's actually writing it, right? There are cases out there where there's open source software that if you look at, that user, that author, they're actually associated with malicious code, right? So is there that connection? Well, if there is, well, they might have actually injected some stuff into that open source and hoping that you're going to download it and use their software. The next thing is talk about quickly is quality, right? What is quality, right? So there's two aspects of quality. It really goes back to the two areas that an enterprise is worried about. One is the value of the product itself, right? And so, the software product perspective refers to the characteristics of reliability, usability, performance, and security. And the other part is the methods and the tools, so my ability to deliver valuable software or quality software. And so traditionally, when programs or offices think about quality and they think about the different parameters of a project, right? They usually turn to negotiating, cost, schedule, and scope, right? The part that one should never negotiate in terms of their triad is really defects or quality, right? Because if I have poor quality, the other three quadrants don't really matter, right? Because my delivery is going to be late, my cost is going to be more than I expected, and while I'll give you functionality, it's defective. So the scope is not exactly what I promised. And from an agile world, they really call this constraints, right? They think these things are fixed. And so if you look at it from an agile triad, right, you have your constraints, right? But then you have this quality over here. To them, it's negotiable, right? And then you have value, right? Problem with this, right? And with that, you have success. The problem with this is that organizations want to deliver the features or a product to customers quickly at a minimal cost. So they really value the value quadrant and the constraints quadrant, and they usually kind of ignore this quadrant over here, mainly because it's actually hard to actually measure and quantify this quality aspect. But quality costs us money, and it costs entire industry, right? So the United States has spent over $2.4 trillion, in a single year on quality issues and poor quality, right? And part of this is security is a subset of that, right? So when I talk about security and I talk about defects from a cybersecurity perspective, what I'm looking at is terms of weaknesses or potential exposures to systems to fail to a cyber attack, right? And it's from flaws, bugs, vulnerabilities, and it can be anywhere in my system, right? It could be part of my architecture, it could be part of my design, it could be part of my requirements. All of these things can lead to a poorly designed and executed system that's vulnerable. Now, many people will talk about these terms of weaknesses, vulnerabilities, and they sometimes use them interchangeably, and they actually do have definitions. Weaknesses is really a mistake or a flaw. That's really the defect that in certain conditions could be exploited by an adversary or turned into a vulnerability. Where a vulnerability is a specific mistake that can actually be exploited. People know how to exploit it, and they've done it, right? Sometimes they refer to these as CVEs and CWEs. You can Google those terms. The reason I focus on quality in a secure by design talk is that studies have shown 1 to 5% of all defects are vulnerabilities, right? And it really adds up. So if you look at Boeing, the Dreamliner, for example, who keeps being on the headlines because of all their quality issues. So I would argue maybe they're not best in class, but say they are best in class, right? Best in class software generates about 600 defects per million lines of code. The Boeing has 14 million lines of code. So I expect them to have about 8,400 defects. 1 to 5% of that is 420 vulnerabilities, right? If they were average, maybe they are, right? They actually have, 4,200 vulnerabilities in their systems, right? F22, you can kind of do the math with that as well. And you can see that there are a lot of vulnerabilities in our software because we produce very defective software. And so the way you address this is really thinking in terms of when are my defects injected, or when are my quality or security vulnerabilities injected in my system, and when are they removed, right? And so software, basically in general, when they're introduced is really in the creative phase, right? They're injected when I'm doing my architecture, when I'm doing my coding, when I'm maybe a little bit in my testing where I'm fixing some defects, right? It's like the 10% range. Most of it's really in that early phases of the software development lifecycle. And that's really where we have to start thinking about security in order to actually build and design and implement more resilient systems. right? Because traditionally, we think about security at the back end, after it's been built, after all the defects, after all the flaws have already been injected into the system, right? But that's where all the money's spent, right? Businesses lose market share when vulnerabilities in the software they sell impact customers and overall productivity, right? If you think about it this way, most major security breaches, what are they named after? They're named after the person who was breached, not actually the person who did the breach, right? Think back, there was a big SolarWinds attack, right? It's named after the company that the attack is associated with, not the actual attacker, right? So it really does hurt your brand, it hurts your reputation long term when it's not addressed. So like I said, just like quality, security is a life cycle challenge. And so most of the things I've talked about and where I'm going to talk about, most people will defaultly think about it in terms of the software development line, the software product, the product actually being built. But the reality is you cannot forget the CI/CD pipeline, right? I kind of already mentioned it once, the whole SolarWinds issue, right? Problem with SolarWinds is that the adversary actually got into their CI/CD pipeline. It was through their CI/CD pipeline that they actually injected their vulnerability into the operational code that's got delivered to various customers throughout the world, right? And it gave the adversary very high privileges because SolarWinds in general, it's an operational piece of software that admins use. And so it had admin privileges, right? And so that software had a vulnerability that actually made lots of other systems who use their software vulnerable, right? And they did that through the CI/CD pipeline. So it's no longer okay just to focus on your application security. And the reality is that it's never been safe to do that, even though we've traditionally done it that way, right? An example of that is in 2014, an attacker caused massive damage to a German steel plant. They basically broke in through their business systems, and through their business systems, they got to the production network, right? They were able to overheat or change the temperature in some furnace, and they actually did physical damage to the steel plant, right? So again, it's not just the cyber world that you have to worry about. The cyber world is connecting us in the physical world, right? Cyber is now running our cars, right? It's running our refrigerators, right? So these things are all around us. The internet is connecting to the physical system. So it also impacts our safety, not just the data breaches and our information and our finances. They can actually physically hurt us, right? For example, right, there have in the past been breaches in the automotive business where someone can actually get into your car while you're driving and turn your brakes on, right? Because your brakes are run by software. They're not run by physical pulleys like they were back in, when cars were first invented. It's all software based. So how do I address that? So when I think about security and the quality attributes, it comes to software assurance, right? Software assurance is really the term used for building secure systems in terms of a discipline, right? And Per Defense has a pretty good definition. It's a level of confidence that software is free from vulnerabilities, either intentionally designed into the software or accidentally inserted at any time during its life cycle, and that the system functions in an intended manner, right? And I highlighted that in both definitions because ultimately what I care about, that the software only functions as intended and it does nothing else by design and by default. And I can't just test that in, right? Verification validation is more than just testing. There's lots of early activities that I have to do to ensure that my system is free from vulnerabilities, but it's more than testing, right? I do peer reviews, I have to do design reviews, I have to do modeling. And so I can't fix every defect. People release software all the time, right? The Boeing Dreamliner is an example. They still released the software and deployed the aircraft with defects in it. So what I have to think about is in terms of what's the risk, right, of delivering this software? What's the chances of a vulnerability or weakness turning into a vulnerability, something that's actually being exploited? And the way I can think about this is through development of an assurance case, right? Because it gives me the ability to reason around my risk and be able to really balance between features, feasibility, and stability, making those trade-offs that I have to make in order to be successful. And so an insurance case, and using insurance cases isn't a novel concept. Maybe if we're using it for cybersecurity, but it's used in safety all the time, right? There's standards, there's processes, there's known techniques for doing this. And what it does is it gives you a structured approach to really make an argument that my system only functions as intended, right? It's free from vulnerabilities and safe to use. And the way you structure an insurance case is by making claims to me for a software product or the whole ecosystem is the software only functions as intended, right? And based on that initial claim, I can create subclaims and I make arguments to support those claims. And then I provide evidence just for my arguments. And then people can throw defeaters at it. Say, well, that's not a true statement. Or what about this scenario? What about that scenario? And you keep going through this process until you have addressed all the defeaters, or you come to the point where no new defeater or idea would change your conclusion or your assurance case that the system only functions as intended. And so what are those engineering practices? How do I begin building that insurance case? How do I start making that argument that my system only functions as intended? So we can just secure by design. And so people are starting to take notice of this. National Cybersecurity Executive Order 2021 basically said that commercial software, it lacks transparency. A lot of people talk about SBOMs nowadays. But how do I build a more secure system by default? There's two definitions here coming out of DHS. I actually like Jen Easterly's definition better, even though it's a few months older than the newer one, right? It's the expectation that technology is purposely designed, built, tested, and maintained to significantly reduce the number of exploitable flaws before it's introduced into the market for broad use, right? This is where we want to get to in terms of secure by design. How do I do that? And so first step is understanding what is my mission? What's my value? Why do I exist? And then think through the full software development or the system lifecycle from requirements all the way through operations and sustainment, maybe even eventually retirement, right? And there's you have a DevSecOps pipeline, building your pipeline, using your pipeline, maintaining your pipeline. And then for all of these things, you have the supply chain that you have to worry about. So if you look at traditional systems engineering V model, what can I do, right? The first step is, mission business analysis, right? So I can do some threat analysis, identify the threats, what are the opportunities for attack, the needs, requirements, what are the actual cyber requirements for my environment? What are the constraints of my environment? Actually write good security requirements and not just say, be compliant with some standard, be compliant with some process, right? Take the time to actually write good requirements that relate to your threats, that relate to your areas of concern, that relates to your value proposition, right? What would be embarrassing? What would be truly impactful if that piece of software, that part of my network was actually successfully attacked, right? And how would one achieve that? How could someone attack me, right? Then I can begin designing around that to avoid or to reduce the risk of that occurring. So it kind of breaks down to like three basic levels, design for weaknesses, code weaknesses, and implementation weaknesses. So requirements, kind of at the beginning. Typical problems with security requirements, right? One is they're stated in specific security solutions or practices, right? Only authorized users to access personal healthcare information, right? Or they're too narrowly focused on a specific application, right? Use SSL for web communications. Compliance mandates, be compliant with this, only maintain logs. Focus on selection of controls after design is complete. So that's too late, right? I need to think about my controls as part of my design, as part of my requirements, because then I'm going to design a more secure, resilient system, right? right? But merely specifying security features is not sufficient, right? I need to anticipate ways in which a system can be misused. I need to perform rigorous threat analysis that's customized to my specific application, to my specific environments in which my application should be used. Define the document and mitigate strategies. So once I understand the flaws, I understand the attack surface, I can begin mitigating those, right? So early specification of security requirements positively impacts fundamental architectural decisions that enable security concerns to be addressed from the ground up, rather added at a late in the date patches in an attempt to remediate security vulnerabilities, right? I want to avoid the vulnerabilities to begin with. I don't want to deal with patches. I just want to have a product that works and functions only as intended. So threat modeling is one technique, right? And the idea here is you really put yourself in the mind of your attacker or your adversary, right? How would they attack this system? How would they misuse my system in a way in which it's designed? If you go back to the initial statistics I showed you, one really showed is that, people don't really get in through network vulnerabilities. They actually get in through your APIs or or a known feature in your application that can be exploited because of a poor design or poor implementation of a feature, right? So you purposely gave your users an ability to do X, but you never imagined someone would use X in some weird way to exploit your system, right? And so that's really, from an Agile's perspective, where I'm constantly trying to add value to my system, I really should take a step back and go, okay, the customer wants this feature. How can I give it to them quickly and maintain value? But how can I do it in a way in which it cannot be misused or abused in a vulnerable way? That's really what threat modeling is trying to get you to begin thinking in terms of your mentality, in terms of the way in which you think about your design, your coding, your implementation. There are different techniques out there. Here's a few of them that have been published. From an Agile perspective, right, I need a role that persona non grata, right? That person who's going to go, okay, if I was attacking this system, how would you keep me out? What are ways in which I could exploit your design? I could exploit this system. And then how would I fit various cybersecurity engineering practices into your Agile lifecycle, right? Talked about threat modeling, right? You should do some risk analysis, do an assurance case, and then your code hygiene, your DevSecOps pipeline. We'll talk a little bit more of that as I progress before you do the release. So one approach is especially for large, complex systems, they're really starting to embrace model-based systems engineering, right? And it's not yesterday's document-centered system. The idea of model-based system engineering is that you use a tool to capture all of your information, all of your data once, and you reference it often. So I begin building views into my system design, views into my architecture based on different perspectives for analysis. But if I change a piece of information here, it automatically gets updated over here on the other side for someone else's view. The value of that is you no longer have the situation where which version of a document is correct, right? We've updated the requirement spec, but we haven't gotten around to updating the design spec. Which one's correct, right? Model-based system engineering really tries to avoid that. It also uses pictures and connections, right? Pictures are worth 1,000 words, and it creates this environment that allows you to do that. When I do that, once I have a model of my system, I can begin using it to identify threats, right? And from that, I can create architectural views. I can model the architecture, find security flaws, and then resolve them at the architectural phase. And how do I do that, right? If I have some architectural views, you can use a workshop, you can get people together. I'm not going to go through every step of this workshop, but the idea is I can systematically work through my model and begin identifying threats to it, right? And here's kind of an example of a threat scenario, right? If I take these parts, right, what's the activity, what's the function in my system, what type of action, is it an insider threat, is it a developer, right? I mean, a developer can be a threat too. They're just not using good coding practices, right? Writing bad software. What's the action they're going to take? What's the attack? What's the asset? What's the effective? And what's the objective? What are they trying to achieve by doing this threat? And then with those pieces, I can build a good statement, right? An insider threat publicly releases the results of static and dynamic analysis to the public to damage the organization's reputation, right? So that's a well-conceived threat scenario. Like begin thinking about how would my insider threat actually achieve this particular scenario? When you do this analysis, when you do these workshops, if you use Stride, for example, you really need to make sure you have the right stakeholders, you have the right skill sets and perspectives. You want the user of the system because they can imagine how the system could be used. Cybersecurity experts who understand vulnerabilities, who understand different techniques that one uses to exploit systems. And then you need the developers and the system engineers because they understand the inner workings of your system better than anyone else. And together, you begin building these models, right? And if you get these slides, you can actually click on these links and actually see a much larger view of this model. So this example comes from our DevSecOps platform independent model. Excuse me, it's a tongue twister. To show examples of how you can do this from an architectural view using model-based systems engineering and so for an activity, say writing code, for example, right? I have this threat scenario, right? But then I can look at like the MITRE KPAC attack surface process and say, okay, how would one achieve this, right? Who is the attacker? Who's responsible for mitigating the attack? And I begin designing my system around this mitigation, around my threat to get rid of it, right? Right, and there has been empirical evidence suggesting that organizations incorporating automated, so quality analysis and DevOps practices will improve your quality. So if I improve my quality, I reduce my vulnerabilities just because of the correlation between defects and vulnerabilities. But I also can be put into different engineering methods, right? So kind of in here in this red, you can kind of see them, right? Here's the threat modeling, right? Secure coding. So I can use good secure coding practices. I can begin doing static and dynamic code analysis tools, talk about in a minute, right? And then I get to the traditional defend your network constructs. Right, so why do I do automated testing? It really reduces the cost. It reduces, it allows for that throughput that one expects in an agile world on modern software development. And so when I think about automated testing from cybersecurity, what should I be doing? And this is a good foundational, a colleague of mine wrote a pretty good blog that explains the different types of testing, but really fundamentally, at a minimum, you should think about, some sort of static analysis tool. It's going to check for bad coding practices, things of that nature. Dynamic, it would be, you're actually running the software and you're trying to attack maybe an API through data transfer and interacting with your system. Do some origin analysis, so that third-party software. What builds the system? What creates the system? And the last one is data security scanning, right? You'd be surprised how often people put credentials in their database. They can get to your database and get the password to your encryption keys, for example, right? And so some basic tools will actually analyze your database and your schema to make sure that you're not doing any of those bad security practices. And then it kind of builds up from there in terms of mobile. It starts integrating different types of tools to get to more integrated advanced testing. And how do you know which ones you should pick, right? Time, budget, most of these tools aren't cheap. Even the open source ones, it still takes time and energy to get them up and running and working, integrated into your pipeline. Your policies, what's your objective, right? Who owns these systems, right? You should think about all these factors. Again, this blog is a pretty good reference to kind of walk you through this. So reality is, we need to be able to build secure software by design, right? That's the expectation that technology is purposely designed, built, tested, and maintained to significantly reduce the risk that someone is going to take advantage of my system or a flaw before it gets to the market, right? And with good engineering tools and practices, you should be able to build a system that's trustworthy, predictable, and timely, right? And balancing those aspects. So I do want to throw a plug to Secure Software by Design is an event coming up in Arlington that we're hosting. There's a call for presentations as well as registration. It's a free event. So hopefully some of you will join us.